Hello guys, welcome to Mars Exploration. My name is Prabhat Fondekar and I'm working here as a rocket design internship trainer. Okay, so we had completed 3 modules. Now the next module is liquid propellant rocket. So we'll start that. So this is a video. So this is an animated video basically. So just see the video, you will get a basic idea and the basic mechanism behind the liquid rocket engine. Okay, so I'll start the video first. Okay, so first part, see, you can see there are the two tanks is present here, right? And in the first class, I have said you that the oxidizer and the fuel are separately stored and both is in the form of liquid, right? So you can see the oxidizer is separately stored here and the fuel is separately stored here. See, this is in the form of liquid and this is a pipeline and this is a fuel part. This is also in the form of liquid. Okay, the next part is a turbo pump. So what is the use of turbo pump? Turbo pump is to just take the fuel part and the oxidizer part from the tank and just spray it to the combustion chamber. Okay. Okay, so this is the green, that orange color indicating the combustion chamber. Okay, so all the combustion process, then the mixing process, so this carried out in the combustion chamber. So the initial part of the combustion chamber means the initial part is attached to the combustion chamber, that is known as a fuel injector. So what is the use of fuel injector? So it's inject the fuel, means it converts the small droplet. Okay, it converts the liquid into small droplet and that droplets now spray in the combustion chamber. See, so this is a injector part and this part is known as igniter. So igniter is used to ignite the propellant. Okay, it will generate a spark. Next one, last one is a nozzle. CD nozzle, converging diverging nozzle. So nozzle is used to convert the heat energy into kinetic energy. Okay, so these are main components in the liquid. Now we will see the mechanism of it, like working principle. So first oxidizer come from this valve. Simultaneously the fuel is come from the fuel tank. And then pump is present here. So pump is just take that fuel and oxidizer part and just send to the combustion chamber. So this is a injector. So injector make a liquid to small droplet. See, like a spray. So it's inject, and next one is the igniter. So igniter generate a spark plug. So that's why combustion process start or burning process starts. See. Got it? So after that, that flame is come from the nozzle part and that thrust generator. Understood guys? So this is a basic mechanism behind it. Okay, now we will see there are the two types of liquid propellant. First one is a monopropellant and second one is a bipropellant. So bipropellant is further classified into the hypergolic one or the non-hypergolic one, and the second one is a storable or cryogenic. Okay, so this diagram we have already discussed in the first module, but we will divide this part. So you can see, as we seen in the video, so there are two tanks present, like first one is for the liquid and the second one is for the oxidizer, and all the connection is present. Got it? And the pressurized, so this is a pressurized, like a pressure feed system will be present here to pressurize the fuel tank or the oxidizer tank. Understood? And the second one, see, except like if you want to, so there are basically two methods for pressurizing any fuel or oxidizer tank. So first method is to that store that pressurized gas into the another part. Okay, another part means another chamber. See, you can see the pressurized gas here, right? And the second one is the pressurized gas is present in the tank itself. See, you can see here like an empty space of tank. So in the empty space, that all the pressurized gas is present there. Okay, so that's known as the ullage. Got it? So that's the two methods. Okay, now the reaction part. So the monopropellant, what is a monopropellant? Monopropellant indicating like mono means single. Okay, so it's only a single propellant is present there, and the next one is a bipropellant. So bipropellant means two parts will be there. Got it? Means two propellant will be there, like two parts will be there, like a fuel part and the oxidizer part. So as seen in the diagram, you can see the first one is only having a one tank for the monopropellant, and the second one is having a two tanks, fuel and oxidizer part. Okay, so in the monopropellant, the decomposition reaction is carried out. What is meant by decomposition reaction? Decomposition reaction means only one reactants and it decomposes into more than two products. Got it? So that is a decomposition reaction. And oxidization reaction is carried out in the bipropellant. Got it? Oxidization reaction means the reaction is carried out with the presence of oxygen. Understood? Okay, so you can see here a catalyst is present. Okay, so what is the use of catalyst? So catalyst will increase the, what is the use of catalyst? Catalyst will increase the stability of combustion. Got it? So that's why catalyst is used in the case of monopropellant. Okay, next we will see, okay, first one is a monopropellant. First we will read the part. Monopropellant by definition are those liquid that have both oxidizer and fuel elements in their molecular structure. Okay, means only one part, and are unstable state that on initiation. Means initially this monopropellant is unstable. So that's why catalyst is used to stabilize the reaction. Got it? The two monopropellants that have been used for the long time, it's hydrogen peroxide and second one is a hydrazine. Okay, so these two monopropellants is very much used in today's industries. Okay, from early stages. What is hydrogen peroxide and hydrazine? Just remember these two names. Then hydrogen peroxide was used in early space missions, was abandoned later due to the problems of thermal sensitivity in the storage and the handling in favor of hydrazine. So it means that like storage part or the handling part for the hydrogen peroxide is very dangerous or it's very critical. Means you have to wear all the glasses, then kit, then gloves, mask. So you have to take precautions while using the hydrogen peroxide. Got it? So handling is also difficult as compared to the hydrazine. So that's why it's abandoned later. Got it? But the hydrogen peroxide is also having some advantages, like it won't releases any toxic gases, so it's known as a green propellant. Okay, hydrogen peroxide is known as a green propellant because it won't releases any toxic gases. Second one is a bipropellant. So as we have told that the bipropellant having the two part, first one is a fuel part and second one is a oxidizer part as seen in the video. So these are some examples of the oxidizers like a WFNA, white fumic nitric acid, then red fumic nitric acid, etc, etc. So these are some oxidizers used in the bipropellant. And next one is a fuel part. So these are some examples using the fuel part as a fuel part in the bipropellant. Understood? And here I have read that like oxidizer means this RFNA, WFNA is known as a hypergolic. So what is mean by hypergolic? Hypergolic means the fuel or oxidizer means, for example, the combustion of the fuel part or the oxidizer, if the chemical is present in that liquid is hypergolic, so it means that for ignition part it won't need any other ignition system. Okay, it won't need any other ignition system. So when they will contact with each other, so they will automatically starts to burn. Understood? So when hypergolic propellant will contact with each other, so they will automatically burn. So that's why they won't need any ignition system. So yes, hypergolic with the number of fuels, the implying that they are self-igniting. So that's why it's known as a self-igniting propellants. And therefore the rocket engine do not need any ignition system. Understood? So that is a hypergolic one. Next, we will see the cryogenic part. So it is a liquefied gases with the low boiling point. With the low boiling point. So you can see the range like a minus 45 to minus 250 degrees Celsius like that at the ambient condition, and the low critical temperature also. Example, the fuel means as a fuel, liquid hydrogen is mostly used as a cryogenic propellant, and as an oxidizer, liquid oxygen is mostly used as a cryogenic propellant. Understood, guys? The next one, then the storable liquid propellant. The liquid propellant which are stable over a reasonable temperature and the pressure range, and are non-reactive with the construction material to permit storage in the closed container for a periods of year or more. It means that some of the chemicals or some of the liquids as used as a propellant, so that propellant it's having a stable range of temperature and pressure, means you can, means in that particular range you can use the that liquid propellant. Got it? So which are stable over a reasonable temperature and the pressure range, and also they are non-reacted with the construction material. Construction material, for example, for storing any types of propellant in a particular tank, so that particular tank is having some material like any aluminium or MS, SS, so there is some material for making that, right? So it won't be react with any type of material, so we can store that for the period of year or more. Got it? Okay, now the desirable properties of the liquid propellant. So it should be having some properties. Yes, if you will make some liquid propellant, so that liquid propellants having these desirable properties. First one is a high energy release per unit mass of propellant. It should be having high energy releases. Understood? Next one, easy ignition. Obviously it having only means it having a easy ignition, so it will be good for the combustion also. Then stable combustion. Okay, stable combustion. If in case the unstable, in case that propellant having the unstable combustion, so that's why it will affect some parameters. Okay, so it should be having a stable combustion. Then high density. So this part we have already discussed in the propellant, solid propellant, right? So if the propellant, the liquid propellant having the high density, so that is mean by like it having a low volume, so you can like store more propellant because it's having a low volume. Understood? Then next one, the should have a good coolant also. Good coolant also means, see, as I have told you in the previous lectures also, that in the combustion chamber the temperature rise is beyond, means temperature rise up to 300, sorry, 3000, 4000 Kelvin like that. So it is very high temperature. Okay, so for cooling purpose, it should be having some property, means that propellant having some cooling property, so it will be good for the motor also, right? So if the cooling properties will be there, then it won't reacted, or it won't miss, the heat transfer won't be affected by the propellant. Understood? The next one is a absence of corrosion effect. Absence of corrosion effect. See, if the corrosion properties will be there, then it will like the material is present in the motor. Okay, so that will going to be corrode. That's why. Okay, that's why it should be having a absence of corrosion effect. Then low viscous to avoid the pressure loss. low viscosity, means that propellant liquid having a low viscosity. If the viscosity will be high, then it will be increases the pressure losses. Okay. Then next one is a low toxicity. It won't releases any toxic gases, so it should be having a low toxicity. Then low cost, easy availability. Got it? So that is a very mandatory thing, like a very basic things. Next one is a method for igniting the propellant. Okay, so in the solid we have discussed some igniter part, right? So in the igniter part we have discussed the pyrotechnic, pyrogen, hypergolic. So there are so many igniters for igniting a solid propellant. Okay, so but there are three methods for igniting the liquid propellant. There are three methods for igniting a liquid propellant. First one is a chemical pyrotechnic igniter similar to the solid rocket engine. Understood? So we have discussed the pyrotechnic igniter in the case of solid. So we can use the same igniter in the liquid also. So that is a one method. Second one is a electric spark plug. So directly we can use the electric spark. So that is the second method. And third method is injection of spontaneous ignitable fuel and the oxidizer hypergolic propellant. Understood? Means the third one is a hypergolic propellant. If we are going to use the hypergolic propellant, so it won't be need any other types of ignition system. So in the case of hypergolic only. Okay, so that is a third part. Got it? Okay, now we will see the injection part. Okay, so in the video also we have seen the injector is present at initially in the initial position in the combustion chamber, right? So what is the use of injection? Basically, injector as arrangement of the injecting propellant into the combustion chamber in the right proportions and the right conditions to yield an efficient stable combustion. Okay, it means that, see, first just see the arrangement in the diagram. In the figure you can see the arrangement. The fuel part is connected here, like a fuel is coming from this side and oxidizer coming from this side. So this is this first chamber small part is like that passage is filled with the fuel, then oxidizer, fuel, oxidizer, fuel. Okay, and then this is a impinging angle. Okay, this is a impinging angle. So from the impinging port, that fuel or oxidizer part will be sprayed. Understood? And then it will contact with each other in the combustion chamber, as you can see in the diagram. Okay, so this is a basic arrangement of the injector. So the fuel part and oxidizer part simultaneously come from that particular chamber and it will injected and contact with each other. So yes, so it should be having a right proportion. Okay, it should be having a right proportion. So just remember that thing. If the proportion is right proportion will be not there, like it should be having basically the right proportion. If the proportion is like varies, so then it will affect the combustion process. Its main function is to break the liquid stream into the small droplets. Got it? Means the liquid, like a fuel part and oxidizer part is already in the liquid part, right? So that liquid is converted into very small droplets. So that process is known as the atomization process. Got it? So this process is known as the atomization process. And further distribute and mix the propellant in the correct proportion. Okay, in the correct proportion. So that is the main arrangement of the injection system. So this is a one part of arrangement. Okay, it is not like a same arrangement. It should be present in the actual motor. So it is a very small type of arrangement. One set of arrangement, you can say. Okay, now there are different arrangement. Like first one is a shower head, then doublet, unlike doublet, etc. So first one is a shower head. So in the shower head arrangement, the oxidizer and fuel is parallel to each other. Means that flow is parallel to each other. Got it? And like doublet means one arrangement of oxidizer and second arrangement of fuel. Okay, that is a like means similarly, means both oxidizer will be contact with each other and both fuel part will be contact with each other, means at same arrangement at the same time, like that is a like one. Then unlike means oxidizer fuel or fuel oxidizer. Got it? The next one is a triplet. So in the triplet you can see the both, see first one is oxidizer, fuel oxidizer. So these types of arrangement, and the pentate you can see there are four different there are four arrangement of oxidizer and only one arrangement of fuel. So this arrangement is basically also depend upon the OBAF ratio, like how much amount of fuel will be there, how much amount of oxidizer if you want, sorry, how much amount of oxidizer and how much amount of fuel you want for your testing. Okay, so that is also important part. Now the injectors. Okay, so there are different types of injectors used in the liquid propellant rocket. Okay, so just see the figure, see the diagram here, you can see. So this is the actual injector. Okay, so this is the actual injector is used in the actual rocket. So you can see there are so many ports is present, right? There are so many small port is present. So this port is used to that liquid is converted into the small droplets. So that's why there are so many port is present here. First one is impinging stream type, then non-impinging or a shower type. Non-impinging means the parallelly, okay, it will go parallelly. Then sheet or spray type and coaxial hollow post injector. So these are some types of injector we are using in the liquid propellant rocket engine. Got it? Then next we will go for the factor influence the injector behavior. Okay, factor influence the injector behavior. Injector behavior means like impinging part also will be there, then the orifice part also, then the propellant combination. So there are so many factors which influence the injector behavior. First one is a propellant combination. So propellant combination means the hyperbolic propellant generally requires the injector design somewhat different from those required by the propellant which must be ignited. It means that there are some types of, or there are some combinations of propellant will be there, so that combinations require a different injector designs. This, for example, hyperbolic. So hyperbolic wants some another types of injector design because it will suddenly react with each other. Okay, means suddenly ignition process started. So in that condition the arrangement is different. Okay, so it's based on the propellant combination also. Second one is the injection orifice pattern and the orifice size. Okay, means like this. Okay, means this is the orifice pattern. So each and every injectors having different types of orifice, different types of orifice pattern, then impinging angle, types of impinging. So there are these small parameters affects the injector behavior. So what are the parameters? We will see that orifice size, angle of impingement, then angle of resultant momentum, then distance of impingement from the injector face, then number of injection orifice per unit of injector face surface area, then flow per single injection orifice and distribution of the orifice hole over the injector surface. So just imagine guys, there are so many small parameters will be there, so these factors will influence the injector behavior. Got it? Okay, next one is a transient condition. Transient condition means it is like a middle condition, not exactly fully ended condition, not exactly a starting condition. So for starting and stopping to permit a satisfactory transient operation. Okay, so this is also influence the injector behavior. Fourth one is a hydraulic characteristics. Hydraulic characteristics means the orifice type and the pressure drop across the injector orifice determine the injection velocity. Okay, means Like for example, so these types of arrangement is present in the actual rocket. Okay, so these types of arrangement having their like a particular orifice diameter, okay, orifice area, understood, that small port area, then the length, the thickness of it, the length of it. So there are so many parameters will be there. Okay, and if the length of that particular orifice will increases, then obviously there will be the more pressure drop. Okay, so this two parameters also affects the injection velocity. Got it? Orifice type and pressure drop. Yes, okay, understood. Then fifth one, the heat transfer characteristics. The lower heat transfer rate are usually obtained where the injectors are designed so that the resultant momentum of the individual injection stream is pointed in the direction of the chamber axis, or when the injection pattern results in an intentionally rich mixture ratio near the combustion chamber walls. Okay, heat transfer. Heat transfer means, like for example, if some quantity, like some combinations is present as a fuel part and the oxidizer part. So obviously first one is atomization process. So after the atomization process, the combustion process started. Got it? And combustion, when the combustion process started, then temperature is suddenly rise. Temperature is suddenly rise, then it will generate the high amount of heat. Okay, and it may chances to heat transfer to the motor part. Okay, motor part means the combustion wall, so it may chances to heat transfer to the combustion wall, so you have to take care of that. Okay, like if the heat transfer will be high, then obviously it will going to be some damage of it. Okay, it will going to be some damage the combustion chamber wall. Okay, so you have to arrange that type of arrangement for a particular, means for the different fuel and oxidizer ratio or the combination, so it won't be affected to the chamber wall. Understood? Then structural design aspect. The injector is highly loaded by the pressure forces from the combustion chamber and the propellant manifold. It means that, see, like the velocity will be there, right? Then it will means the fuel part and the oxidizer part will move from the tank to the injection, move from the tank to the injector, and suddenly injector, what is the use of injector? So it will inject the propellant at some velocity. Okay, at some velocity, so velocity will be increases, so at that point obviously the pressure affected. Okay, so pressure is also affected, so this pressure and some stresses, then strain, then some force will be there, so these parameters is affected or influence the injection design. Understood, guys? So this pressure, then forces, then stresses, so this some parameters is affected the injector design. Then combustion stability, yes, as I have told you that it should be having a stable condition, means the combustion having a stable condition. If you increase the length of the hole, if you increase or decrease the diameter of it, or if you increase or decrease the impinging angle, so these small parameters is very affected to the combustion stability. So it should be having a particular design. Okay, it should be having a perfect design, so then and then only the combustion process will be stable. Understood? The injections holes pattern, then impingement pattern, then hole distribution, then pressure drop, so this having a strong influence on the combustion stability. Got it? So that's why the combustion stability is also important factor and influence the injector design. Okay, then next one is a combustion process in the liquid rocket. So this is basic. Okay, sorry. So in this diagram you can see this is the injector. See, this is basically indicating the combustion chamber and the nozzle part. Okay, so first one is injector. So injector is used to inject the propellant, so you have already know about that. And atomization, what's the use of means, what is meant by atomization? I have told you in that slide, previous slide. Atomization means the process to the means process of making a liquid to the small droplet, so that is an atomization. So the first one is atomization zone, or you can say the injection zone. The second one is a rapid combustion zone. Rapid combustion zone means the suddenly, like for example, if the fuel part and oxidizer part will meet with each other, or like contact with each other, then obviously at that point, means after that point, the combustion process started. Okay, means ignition started. So that's why, like at that time, the combustion suddenly started and suddenly increases the temperature or the heat also. So that's why it's known as a rapid combustion zone. So in that particular zone, the combustion process is very rapidly happen. Next one is a stream tube combustion zone, means after some portion, like after some patch, the combustion process will be like very like means the combustion process is maintained. Okay, maintained means all the flame, all the gases or all the flames is now moving with the stream tube. Okay, moving with the stream tube, and that's why it's known as a stream tube combustion. So then the stream tube combustion or the steam tube gases is then move towards the nozzle part. Okay, move towards the nozzle part, and after that obviously exhaust. Got it? And here you can see the transonic flow zone. What is meant by transonic flow zone? Transonic flow zone, you have already know about. I think this terms is you are familiar with these terms, like a subsonic, transonic and supersonic, hypersonic, like that. So transonic means the Mach number range is between 0.8 to 1.2, like that. Okay, means in this portion you can see the velocity of that flame, or you can see velocity of that gases, it's nearly equal to that range. Okay, so that's why it's known as a transonic. And after that, the velocity is going to be increases, and the velocity now it's supersonic velocity. Okay, means near about that supersonic velocity. Understood? Okay. First one is a inject. Yes, we have already discussed this with the help of diagram. Injection and atomization. So the liquid are atomized into a large number of small droplets. The heat is transferred to the droplets by the radiation from the very hot rapid combustion zone, and by the convection from the moderately hot gases in the first zone. Got it? So in this zone, the atomization process is carried out, and the heat is going to be increases after this combustion zone. Okay, means in the atomization zone means after the atomization, like suddenly combustion process started, right? So that's why heat is going to be increases. The rapid combustion zone, the intensive and the rapid chemical reactions occur at increasingly higher temperature. Got it? Increasingly higher temperature means rapidly or suddenly the chemical reaction is occurred. So that's why the temperature is also going to be increases suddenly. Any remaining droplet are vaporized by the convectivity. Okay, any remains, if the droplet will be remains in that portion, is if in case, okay, if in case the droplet will be remains at that portion, so it will vaporize by the convectivity. Got it? Then last one is a stream tube type. Then oxidation reaction continues, but at the lower rate, and some additional heat is released. The chemical reaction continues to attain the equilibrium composition. The streamline are formed, and thus the little mixing of propellant. Got it? Means in the stream tube combustion zone, the streamlines flames are formed. Understood? Okay, so this is all about the combustion zones. The next one is a combustion chamber. So there are certain parameters and certain parameters will be there. So we have to consider that while designing. Okay, so if you want to design any combustion chamber, so you have to take care of the three designing parameters. First one is that shape, means shape of that combustion. Second one is a volume of that combustion chamber, and next one is a load and stresses. Got it? So first we will see the shape. So there are wait a second, yes. So there are three different conditions or cases. First one is a long chamber and the small cross section. Long chamber means the length of that chamber is large, but it having a small cross section, means the diameter of that circle or the diameter of that cylinder is small. So that is the first one. So obviously if you increases the length, then it will affect the pressure losses. Okay, it will affect the pressure losses. If the length is increases, then the pressure losses is going to be increases. The limitations on the injector design to accommodate the desired number of injection element. Got it? So that's why it will limit, so it, the injector design to accommodate the desired number of injection element. So means like if the small cross section will be there, so only small pores orifice of the patterns of that orifice will be reduces. Okay, so it is also affected the combustion process. The short chamber and the large cross section, it is reverse condition of that. Means now the length is short. So if the length is short, so there is no chance of pressure loss, means the pressure loss is reduced. But if you decrease the length of it, then the means first just imagine that part. So there are three types of zones will be there. Okay, so it is very like congestion. Okay, very congested area, like each zone having some particular area. So if you increase the total area or if you decrease the total area, so it will affect the zone area also. The propellant atomization and the vaporization zone occupy a larger portion of the combustion chamber volume. Mixing and combustion zone becomes too short for the efficient combustion. Understood? So if you decrease the length of the chamber, so it will affect the zone area also. Okay, it will affect the portion of that zone. So obviously after the obviously atomization takes some portion of the combustion chamber, right? So then suddenly the stream tube, okay, means after that atomization means there are two zones will be there. So that two zones that means you can say it will congested. Okay, it will congested, not a specific that zone will be there or specific area is present for that particular zone. So it's not like that. So that's why it should be having a enough area for doing all the processes. Understood? And the last one is the other factors like heat transfer, combustion stability, then weight are also considered in determine the final combustion chamber configuration. Okay, so just remember this all the parameters, all the factors. So then and then only you will design, is you can design any particular combustion chamber. Second point. Okay, next one is type of chamber. Okay, so there are basically three types of chambers. Like first one is a spherical, then second one is a near spherical, and next one is a cylindrical. Okay, so spherical means the combustion shape, means the combustion chamber having a spherical design, like a circle, that ball like, you can say football like spherical design. Next one is a near spherical. So this picture, you can see the picture. So this is like a near spherical. Okay. Next one is a cylindrical chamber. Cylindrical chamber means like this. Okay, it's having a only cylindrical chamber. Got it? Okay. Then next, these are some parameters. So just see these terms. First one is a combustion chamber area ratio. combustion chamber area ratio. So it's denoted by the epsilon C is equal to AC by AT, means the combustion chamber area divided by throttle area. Okay, so that is one formula of it. Then the combustion chamber volume. So this is the chamber volume formula. So if you want to calculate the chamber volume so you have to know about this all the particular terms like A1, AT, then L1, LC, means L1 is indicating the cylindrical length. Okay, then A1 by AT indicating the chamber contraction ratio. Got it? Area, initial area by throttle area. Then LC means the length of that conical frustum. Okay, length of that conical frustum. So these are some parameters you have to know for calculating the combustion chamber. Okay, next one is a theoretically required combustion chamber volume or function of. So this is also one formula of volume chamber, like Vc is equal to m dot V into Ts. M dot means mass flow rate of the propellant. Okay, means any propellant having their particular mass flow rate, right? Then next one is a V. V means chamber volume. Okay, V means that specific volume, sorry, not a chamber volume, this is the average specific volume. Then next one is a TS. TS means the stay time. TS means a stay time. Stay time means I have put the definition of it also, like it is average value of a time spent by the each molecule or atom within the chamber. What it means, there are so many number of molecules is randomly moving in the combustion chamber, right? So the stay time means the average value of the time spent by the each molecules or atom within the chamber. Got it? Next one, okay, so it's having some range also, like a stay time. This is a range of the stay time, like 0.0001 to 0.4 second for a different types of chamber and the propellant. Okay, let's just imagine that like only in the fraction of second is each molecules is moving in the combustion chamber for a very particular fraction of second, like 0.001 to 0.4. So you have to take average of all the time, then you will get a stay time. Got it? So these three factors, like average specific value, then mass flow rate and the stay time. So these three parameters is directly proportional to the Vc. Vc means chamber volume. Understood? Okay, then characteristics length. The characteristics chamber length is defined as the length of chamber, okay, of the same volume would have if it were the straight tube and had no converging nozzle section. Means in some motors or if in some condition, in some engine, there is no converging nozzle is present. Okay, there is no converging nozzle is present. So in that condition, so if the converging part will be not there, so you have to calculate the characteristics chamber length. So it is the formula of it is Vc divided by AT, like the volume of that chamber divided by throttle area. So you will get a characteristics chamber length of that particular engine. Got it? Next one, yes, range of it. So this range is between 0.8 to 3 meter for many biopropellant systems. Got it? So this range is 0.8 to 3 meters for a different bipropellant engines. Next we will see the selection of the volume and the shape of the combustion chamber. The volume has to be large enough to adequate mixing. Okay, I mean, for example, in the previous slide we have discussed like a small volume, big means larger lane, small lane. So these small parameters is very affected. So if the volume is not large enough, so that means in that condition the mixing process, evaporation process means, or the combustion process will not perfectly carried out in that particular chamber. Okay, so that's why it should be large enough to adequate mixing, evaporation and complete the combustion for the of any particular propellants. Then chamber diameter and volume can influence the cooling requirements. Okay, as I have told you that cooling part is also required for the particular chamber. So the cooling part is also affected, means influenced by diameter and volume also. Then all inert components should have minimum mass. So if the mass will be reduced, so then is when you calculate the total mass, so it will going to be reduced. Okay, so that is a good thing. The next one is a manufacturing consideration favor the simple chamber geometry. Okay, it should be a simple geometry. If this geometry will be simple, then obviously the combustion process is tends to be simple. The gas pressure drop for the accelerating the chamber combustion chamber products within the chamber should be minimized. Okay, like as I have told you, if you increases the length of that chamber, then obviously the pressure drop will be increases. Okay, so this factor is also important. So it should be having a minimum, the pressure drop having a only minimum value. For the same thrust, the chamber volume and the nozzle throat area become smaller as the operating chamber is increases. Okay, for same thrust. For example, if you want to, if you want if you are doing some testing, okay, so from one testing, after one testing you have got some results, got it, you have got some results, but now if you change the parameters, then obviously you will get a different result. But if you want the same results, so then either you have to increase the chamber volume or increase or decrease, or you have to take change the throttle area. Okay, like the chamber volume and the nozzle throat area become smaller as the operating chamber is increases. Okay, means if you increases some quantity, then you have to decrease the other quantity, then only it will balance, right? Okay, then third parameter is chamber wall loads and stresses. Okay, for pressurization, for injection, for combustion, means like this process. So after these processes, you can see there are so many loads, stresses is formed. Okay, so many loads and stresses will be formed in the combustion chamber or the injection part or in the nozzle part also. The component are strong enough to carry all the loads. That is a very basic thing, like it should be having a strong enough to carry all the loads. Yeah, like if the material is not very strong, so then it will damage it. The walls are subjected to rapid and axial load from the chamber pressure, flight acceleration, vibration and the thermal stresses. Okay, there this parameter is also there, like a chamber pressure. Chamber pressure is also varies. Then flight acceleration is also there, vibrations, thermal stresses. There are so many different performance parameters, different factors is present when you are doing any particular test. Okay, so it should be strong enough to carry all these or maintain all these, sustain all these stresses. Valves also have to withstand a momentary ignition, pressure, surges or shocks. Okay, means as I have told you that the injection velocities goes beyond the Mach number, like a supersonic velocity. So after means when you are go beyond the supersonic, so it means chances to produce the shocks. Okay, so obviously when the shock will be produced, so it will affected the walls or any particular chamber, right? So in that condition it should be stand enough to sustain all the shocks. Okay, so that is also important part. Okay, now the last part is a tank. Now we had already discussed about the injection part, then igniter part, then chamber part, nozzle parts, all part we have already discussed. Now the last part is a tank. Okay, the propellant bipropellant tank. So there are two conditions. First one is a bipropellants. For bipropellants, like there are two tanks will be present and the oxidizer and fuel are separately stored. So that's why the propellant are stored in one or more oxidizer tank and one or more fuel tank. Then next one, for the monopropellant, store in only one tank. And tank design are used to control over the change in the location of vehicle's center of gravity. Means in the figure you can see, just imagine the weight of tank. So it is having very high weight. Okay, as compared to the propulsion system, like the tank weight is very high. Means all the oxidizer is present in the tank or all the fuel part is present in the tank. So that's why the weight is very high. So when you change the, like in the stable condition, so in the first module we have discussed the stable condition for the CG and CP, right? What is the stable condition? The CG location, it should be having the upper position as compared to the CP location. So if it won't be there, so then you have to change the location of tank, because the more quantity of the weight and more percentage of the weight is acquired by the tank. So that's why if the stable condition will be not there, you have to change the location of tank, so it will affect the center of gravity location. Okay, now next one is the ullage part. Okay, so you, what is mean by ullage? So in that second slide, I think, yes, in the second slide we had discussed about the ullage. So ullage means some quantity of the pressurized gas is present in the empty tank. Okay, not empty means empty space in the tank. The extra volume of the gas above the propellant is sealed tank. Extra volume of the gas above the propellant in the sealed tank. The ullage volume is between the 6 to 10% of the tank volume. Okay, means only 6 to 10% of the total volume of tank. Then it depends on the storage temperature range. Means the ullage part is depend on the storage temperature range and the propellant coefficient of the thermal expansion. Okay, means the temperature factor, then the what is that, yeah, what is that, the coefficient of thermal, means these factors is affected the ullage part. Okay, so you have, when you are designing the volume of ullage or particular section of ullage, so you have to first consider the storage temperature range and the coefficient of thermal expansion. So then and then only you can design that. The last one is the tank material. The aluminium, stainless steel, titanium, alloy steel and the fiber reinforced plastic. So these are some material we are using for manufacturing any tank. Means for example oxidizer tank, fuel tank, like that. Understood guys? Okay, so finally we have completed the fourth module. So in that module we had discussed all, each and every terms, each and every parameters related to the liquid propulsion system. Understood? I hope you got all the information and knowledge. Got it? So next one is a hybrid propulsion system. So in the next module we will discuss that. So thank you so much guys. I hope you got the video. Thank you so much. Bye bye.